So students, we are going to continue with our same discussion. So in that, what actually we are going to learn is, we are going to see the definition of your attenuation and the concepts of your losses. So we are going to continue with that concepts and how it is effectively going to be used for us. So these all we covered in the previous sessions. So we are not going for further clarification of those. Attenuation also we talk about how the attenuation is used, what is attenuation of meaning of that. Attenuation formula is what, students? Output power by input power to the given length. That is what attenuation, right? The ratio of the optical output power to the input power in the fiber of the length L, that is called as attenuation. The various losses in the cable are due to the absorption, scattering, bending and dispersion. Because of all these parameters, you got the attenuation factor. Similarly, what is the bending losses depends upon two parameters. One is macro, another is a micro. Macro is what? Micro is what? It causes because of the fiber which undergoes bends, and it is not going to reflect affect the core, but it's going to affect the cladding, right? This is called macro. Micro means it is going to affect both core as well as the cladder. So this is called it as micro. Similarly, next kind of losses we do have for that would be this diagram also we covered in the previous session, so I'm not going into detail of it. Now we are going to see the absorption losses. So what is absorption losses? It is out of two types, intrinsic and extrinsic. Intrinsic is what? It is when we are not adding any doping to that fiber, when we are not adding any other impurities, then it is intrinsic. Intrinsic caused due to the interaction with one or more component of the glass. In the glass itself, you get the one or more component. Because of that, if you will get the absorption loss, that is called intrinsic. What is extrinsic? So extrinsic is what? It is due to the impurities because of adding of chromium, iron, cobalt, copper. So because of these all kind of ions, if you get any kind of impurities, and if you add it in that water, if you get that particular absorption loss, that is called it as extrinsic. Intrinsic occurs when photons interacts with electrons in the valence band. And excitation, it is to higher energy level near the UV range. So it is used for ultraviolet. This is for infrared. Next is what? Scattering loss, students. So what is basically scattering, students? It occurs due to the microscopic variations. Microscopic variation, what I'm saying, whenever we want to see the any particular light, you will not see that particular light in a one direction because your eye has some sort of defect, like you can't see that particular angle. So it vary from one eye to another eye of vision. So that is what, when we see from microscopic variation in the material, because of materials may be made up of different parts, so it can have the different density, compositional fluctuation might be there, the structure in homogeneities will be there, and manufacturing defects will be there. So because of all these kind of thing, it may occurs based on that. So the linear scattering occurs due to the relay scattering losses, my scattering losses, waveguide scattering losses. So these are three losses you'll get, students. That is linear. Non-linear, students, it is because of the stimulated beryllium scattering and stimulated Raman scattering. Because of these all parameters, may get that particular scattering effect. So based on that, you may get the scattering losses. So once we get the scattering losses, it also occurs based upon the phenomena of linear. So basically now we are going for linear scattering. So basically, students, what is the meaning of linear scattering? It occurs because of relay scattering losses. These losses are due to the microscopic variation. As we said just now that the variation whatever we do have, it is based upon the microscopic. So whenever we take the microscopic variation, because of the unequal distribution of the molecules with respect to the density factor, whenever we want to see any kind of those parameters, we get the losses, right? So what is this losses all about? This losses is all about the variation. Whatever the variation we do have, based upon that variation, the losses are occurring because of microscopic material of the fiber. That is also one of the things. Second thing, unequal distribution of molecular densities or atomic densities leads to the relay scattering losses. Because of that also you may get the relay losses. Next part, because the glass is made up of several acids like silicon dioxide, phosphorus, pentaoxide, etc. This glass is made up of different acids, right? So if you want to see that composition, fluctuation can occur because the materials are different. So whenever the materials are different, the fluctuation can occur because of these several oxides, which rise to the relay scattering losses. Because of these all phenomena, we can say that the losses whatever we are occurring because of the scattering losses, right? So this is what one of the example of relay scattering losses. So we need to understand in detail of it why we get that losses. So first thing is that because of microscopic variation in the material. Second thing, unequal distribution of the molecular densities, because molecular densities are not the same, or glass atomic densities leads to the relay scattering losses. Third point is glass is made up of several materials, several acidic materials such as phosphorus pentoxide, silicon dioxide composition, and that fluctuations that can occur because of these several oxides which rise to the relay scattering losses. Because of all these parameters, you may consider that that particular losses is nothing but the relay losses. Second part of loss in the scattering is what? Mia scattering losses. What is Mia scattering loss, students? So these losses results from the compositional fluctuation and the structural in homogenerics and defects created during the fiber fabrications causes the light to scatter outside the fiber. So basically this completely is all about the outside, not the inside the fiber. So these losses results from the compositional fluctuation. What is the meaning of that? Whenever we do have a structures, it may have the same formula, but the structures are different. My meaning is that the material can be same, but the kind of designing, whatever we are putting, all the designing may be different because of the different diameters of the core, imperfection of the cladding, and change in the Ri of their core or cladder, refractive index of the core or cladder is varying because of the materials whatever putting. All these things, because of that we get the second type of losses, waveguide scattering loss. So Mia scattering loss is because the compositional fluctuation and the structural inhomogeneity and defects created during the fiber fabrication causes the lights to scatter the outside the fiber. This is occurring outside the fiber. Whereas the waveguide scattering is occurring, it results of variation in the core diameter, imperfections of the core cladding interface that change in refractive index of either core or cladding. So maybe the core is different or cladding is different. When it is going to change from core to the cladding, it may result into the waveguide scattering. Waveguide scattering is completely depends upon the refractive index changes of either core or cladding. This is about your linear students. So next part we are going for scattering, next type of it, non-linear. So basically students, what is the non-linear? Non-linear is all about your SBS scattering. What is SBS stands for? Stimulated Brownian scattering may be regarded as the modulation of light through the thermal molecular variations or vibration within the fiber. This is inside the fiber. We are getting in that we are going to get that inside the fiber. Okay, so we are going to get that based upon that. Non-linear scattering is because of the SBS scattering, student. That is SBS stands for stimulated Brillouin scattering that may be regarded as modulation of light through thermal molecular vibrations within the fiber. So inside the fiber only it is going to occur. So in that the basic thing what we are going to see is PB. Formula for getting that particular scattering is PB is equals to 4.4 into 10 power minus 3 d square lambda square alpha in dB. Volt watts. This is our power, right? We are finding the power in terms of watts. What is V actually? V is nothing but source bandwidth in gigahertz. So we are seeing the V, not volt, it is V actually, the source bandwidth. What about D stands for, students? Fiber core diameter in micrometer. Lambda is what? Operating wavelength in micrometer. So these are the parameters we do have, students. So the next kind of scattering, student, is RSRS. What is R stands for, student? It is what? Raman. Simulated Raman scattering is similar to the stimulated binomial, whatever we do have this part, right? This formula and the previous one. Both Brillouin scattering. Both are the part of non-linear scattering. So this stimulated Raman scattering is similar to the simulated Brillouin scattering, except that high frequency optical phononian rather than the acoustic phononian. Phononian actually what, students? So the material which we are adding inside that particular material, that's because of that we get this particular scattering. So this is scattering formula is what? PB is equals to 5.9 into 10 power minus 2 d square lambda alpha dB watts. So we do have alpha dB in watts. Because of that we will get 5.9 is the constant value. D square is what actually, students? It's the diameter of the core. Alpha is the wavelength. Alpha is nothing but the whatever attenuation we are taking it in terms of decimal we are considering. What is phonon, students? This is the collective excitation in the periodic arrangement of atoms. So what actually we are taking? We are taking the complete atom. We are taking a periodic arrangement. In the particular arrangement we are arranging atoms or molecules in solid. So always we try to take that phonon in solid only, because the collective excitation, whatever we can do it in terms of periodic scattering. Periodic atoms and molecules we put it and we can try to take in terms of solid only. Because of that kind of scattering is called it as, there are two types of it. One is linear and another is non-linear. In non-linear we have learned about SBS and SRS. Both are come under the non-linear part only. Next part we do have student dispersion loss. So next kind of the loss we are going to learn after scattering is dispersion. In dispersion, as an optical signal, whatever the signal we are considering that travels along, which side it is along the fiber, because it becomes increasingly distorted. Distorted means it try to move from one end of the material to the another end. It's completely distorted, not in a proper form, because the signal may travel from along the fiber only, right? So whenever we take a fiber, the signal may varies from one end to the another end. Whenever we try to take that particular material from one end to another end, we get that distorted form. That because of that, this distortion is a sequence of intermodal and intramodal dispersion. So the types of intermodal and intramodal, what are the particular distortion we are going to see now. So first thing, dispersion loss is all about the increasing distortion because of the signal we are passing through the optical fiber only. Whatever the fiber we do have students, because of the fiber itself, we are trying to take that particular element to it. Because of that, you get the distortion, that is called as dispersion loss. So this distortion is a sequence of intermodal and intra. So what is the two types of these models? We will going to see about it, how the intermodal and intramodal is going to be used for this particular dispersion. First one, intermodal means students, pulse broadening due to the intermodal dispersion results from the propagation delay difference between modes within a multi-mode fiber. Within the mode only, we are considering the multi-mode. Multi-mode means instead of using one mode, we are going for the multi-mode fibers. Because of that, the kind of intermodals, whatever we are getting, that is called it as intermodal dispersion. What about the intramodal students? So this, it is a pulse spreading that occurs within a single mode. In the one particular mode itself, it is going to get that pulse spreading. So pulse is going to spread that occurs within a single mode. So because of the material dispersion, because of the waveguide dispersion. So this is also one of the type of dispersion that is called it as intramodal dispersion. So intermodal dispersion as well as the intramodal dispersion we have learned, that is also two type of dispersion losses come under the dispersion losses. Next part is about dispersion. We have seen what are the things this consists of. Next part we are going to see after the dispersion losses is what is these two types of dispersion. As we said, it is about material dispersion, right? Here we do have material and waveguide. So what is material dispersion? It is also known as spectra dispersion or chromatic dispersion. Because of the spectral line, you may get the dispersion, or because of the chromatic dispersion, you may get the distortion. Because of these two parts, it is also known as that name spectral dispersion or chromatic dispersion. Results because of variation due to the refractive index of core as a function of wavelength. So whatever the core we are considering, it's become the function of the wavelength, because of which pulse try to spread occurs even when different wavelength follow the same path. Whenever we see this difference of that particular wavelength, it's also going to follow the same path. So that spreads occur even when different wavelength follow the same path. If you take different wavelength, but it is going to follow the same path only. So because of that, the all will get immersed inside one particular material, right? So that also you will get because of the material dispersion. It's getting distorted for that. Next part is what? Wavelength dispersion. So whenever any optical signal is passed through the optical fiber. So whenever we try to pass any signal through the optical fiber, practically 80% of optical power is confined to core and rest 2% power move into the cladding. So what is the meaning of that? If you give 100% signal, 80% is taken by core and 20% is taken by what? Cladding. So because of that, the kind of wavelength will varies, because when we try to make into that, so because of that the waveguides you will get the disperses because of the core and cladder consumption of the signal, right? So that is also called as waveguide dispersion. So now student, till now we covered the losses because of the dispersion, losses because of the scattering, losses because of the bending, losses due to the variation in their material, in their excitation methods, in their particular directional method. Because of all these parameters, you may get the losses and you understand about it SBS as well as SRS. SBS is stimulated Brillouin scattering, SRS is simulated Raman scattering. So that is also two type of scattering we have discussed, which we are having in our scattering part, Mia scattering and waveguide scattering. Waveguide scattering is further part of SBS and SRS. And then we have learned, before that we have learned about your relay scattering as well as. So scattering are of two types, one is linear, another is non-linear. In linear, what are the things covered? Relay scattering, Mia scattering, waveguide scattering. Non-linear, SBS and SRS. That is come under those two particular scattering, right? Next, we have learned about absorption. Also in absorption, we have seen about intrinsic and extrinsic absorption. Why we get that particular part, why we get the losses, because of the impurities which we are adding, and it's resulting in the dimming. Dimming means the light intensity will be decreased. Dim it is. Dim of the light at the end of the fiber. So this is because of that it also occurs. These all factors we covered in today's session. So in the further part, we will proceed with how we going to get that linear, how we going to get the linear scattering, how we going to get non-linear. This also we covered, and we covered about absorption losses also. Now we are proceeding with the laser, how the laser is useful and why we get that. So now we are going to see the light source, right? So light source is first thing. Your light source, how we get the light source for that, our optical fiber. So we are considering first is LED, light emitting diode. So what is light emitting diode? Is made up of materials such as your gallium arsenic phosphates, your whatever the elements we are considering, that is because of the hole and electron recombination. You have seen the details about in your electronic devices part when we see the LEDs and LCDs on everything, right? So here we are using the application part of it, how it is going to use for light source. So now second part we do have to see is ILD. What is ILD stands for? Injection laser diode. So this is also one of the laser diode we do have. It is called injection laser diode. So where actually these light sources, how many types of light sources as of now we see? Two. One is LED and there is ILD. LED is made up of such material as gallium arsenide and gallium arsenic phosphates. Your light is emitted when holes and electrons will combine, we'll get that LED, and ILD will get when we get similar in construction as LED but ends are highly polished to reflect photons back and forth. So if we want to get the photons, right, because light produces the photon, right? So we will try to polish that one. We try to make that polishing to that ILD so that we'll get the photons to get back and forth. Try to get a proper direction for our photon to move from forth and back. Because of that, we are going for this particular material, that is what? ILD, injection light source of the laser. Next part, light emitting diode. So basic, how do we get the light emitting diode? We are going to see that. So light emitting diode or LED is what? Normally we can see this bands, right? As you can see in the diagram itself, we had LED diagram. This is what physical nature of it. This is what how it is internally going to get that. We'll take P type, we'll take active region, N type substrates, electrons in holes. We'll try to take that, and we'll what actually we are going to combine. We're going to combine by considering these layers. Upper side, what we had, the normally we had conduction band. In any particular bands, we do have three bands, right? Conduction band, valence band, and semiconduction middle band, right? So the normally empty conduction bands of semiconductor populated by electron injection into it by forward current through the junction, and the light is generated with electrons recombined with holes. So electron try to recombine with the hole. This the mechanism by which light is emitted from LED. So this is the mechanism the light is going to emitted from LED, and you get these regions. So you get anode, you get the cathode. The longer is what? Two ends we do have for LED. One is longer and the shorter, and we get this substrate diagram. You should draw it and write about the basic construction. So what is the basic construction? Electron and hole will try to recombine, and it will be used to inject the electrons into the forward current through the junction. So this is just a mechanism by which light is going to enter for the LED, right? So for fiber optics, the LED should have high radiance, means the light intensity should be very high, fast response time, and high quantum efficiency. These are the three basic essential needs for light emitting diode. If they fulfill these all, then that LED will be useful for our optic fibers. Similarly, LED structures. Based upon that, how many types of structures we are going to see? The first is planar LED, second is dome LED, surface emitted LED, edge emitted LED. These are the three to four different types of LEDs we do have. We are going to see about it, how this LED is going to work on that, and what are the essential elements that LED should follow, and how it is going to work on that. So these are parameters we need to consider when we try for LED structures. So this internal structures and the diagram of these particular LED structures will proceed now. So the first is planar LED. So what is used? The diagram of planar LED you can see from the diagram, students. As you can see here, the planar LED is, you can see there is a N-type substrate is there, there is a P-type substrate is there, there is a equiaxial layer is there, there is a ohmic conductors. So ohmic means which obey the Ohm's law. So Ohm's law obey by the only conductors, no? Ohm's law could not obey by the semiconductors. So because of the non-linear nature, Ohm's law did not explain. Ohm's law only explained about the linear nature. It did not explain about the semiconductors. So the planar LED is the simplest of structure that are available and is fabricated by either liquid or vapor phase epitaxial processes. Means by using that particular processes only, this is going to made up of. So over the whole surface of gallium arsenic substrates, that involves p-type diffusion. As you can see in the diagram, there is a p-type diffusion into the n-type substrate. This is our substrates, right? From there, it is p-type diffusion we are putting from the n-type substrate in order to create the junction illustrated in figure. This is a junction which I have shown in the figure. The forward current flow. What is the forward current flow? Flow from the where actually junction, right? Gives Lambertian spontaneous emission, means completely try to give the light output from here. And the device emits the light from all the surface. This device is emitting the light from all the surface. However, only one limited amount of light escapes the structure due to total internal reflection, and therefore the radiance is low. Because of that, the radiance is getting lowered for that particular element. This is about one particular part. Now, one of the example we have seen. Now we are proceeding with laser and the function of laser. So basically, what is laser full form, students? Light amplification. So what we are doing? We are doing the amplification of light by stimulated emission and radiation. By applying the stimulated emission of the light, and we try to get the radiation from the laser. So this can be done by using coherent light stimulated emission, narrow beam width, because beam width needs to be very less. Beam width to be, so the kind of beam width whatever we are considering, that needs to be very narrow, because to get the more focus. If the width is becoming lesser, the kind of light intensity will be more. Second is high output power, because we are applying the amplification. What is amplification? Increasing the strength of the signal, right? So the narrow line width, because only few wavelength will experience the positive feedback and get amplified. How it is getting amplified? By keeping into narrow line width, because only few wavelength will experience a positive feedback and get amplified. It start getting amplified by considering the optical filtering. So by considering that, it is going to work on it. So as you can see in the diagram, students, so in the diagram what it have, we had a waveguide, semiconductor laser light. See, beam width is very thin, right? And it is tapered by the fiber, an anti-reflecting coating we are keeping, and we are considering the taper over here. Whatever the taper is consist of, it's for second fiber. This is our waveguide. So by considering this waveguide, your light intensity is getting increases. In laser, what are the things we get? We get the absorption. What are the absorption? An atom that in the ground state might absorb a photon emitted by another atom. So when it is in ground state, try to observe the atom, because atom can be in two states, right? One is in ground state, another in the excited state. So when the atom in the ground state, it try to absorb a photon which emitted by another atom. So thus making an transition to an excited state. So try to make a transition to the excited state. So because of that, you get the absorption of light. Spontaneous emission. So what is a spontaneous and stimulated emission, students? The spontaneous emission due to the photon, random emission of photons, which enables the atom to relax the ground state. So it will be in the ground state. Whenever the random emission of photons is occurring, because in the ground state, it is called spontaneous emission. stimulated emission, students? An atom which is in excited state might be stimulated to emit a photon by another incident photon. When it is one incident photon is occurring, because of that there is one more incident occurrence happening. Because of that you get the stimulated emissions. So that is what you get. The part is called stimulated emission. Stimulated emission for excited state, spontaneous emission is for ground state. So because of these two particular states you get the emission of photons. So when in spontaneous, random emission of photons because of relaxed ground state. Stimulated emission means what, students? Which actually get the excited state because of another atom. It is getting incident on it. It's getting the photon emitted. That is what stimulated emission. This is occurring in the laser, as we have seen in the diagram only, right? So in absorption is occurring because of two tapered fiber 2 and fiber 1. As you can see here, the semiconductor part laser chip is there. As you can see, anti-reflecting coating we are keeping so that it should not get reflected. Here we have first taper, here we do have second taper. We are trying to see that how it is going to occur, that taper, by considering the laser absorption, spontaneous emission, stimulated emission part of your laser, right? That is about the laser we have seen. This is the laser about. So the laser features are what? It should be coherent light because of stimulated emissions. It should be narrow beam width because of very focused beam needs to be there. It has high output power because of the amplification factor. We are considering narrow line width because only few wavelength will experience the positive feedback and get amplified. All will not get amplified, only the few will get amplified. So because of the optical filtering. Okay. Next is light detectors. What is a first light detector, student? It is a pin diode. So pin diode is used for detecting the light. So in that, how the pin diode is working. So just see here in the diagram, there is a P substrate, there is an M substrate. Inside there is a region, that is we are considering as what? Diodic region. We are putting what? We are passing the photons which are going to absorb in the intrinsic layer. So whatever the intrinsic layer we had, the photon is getting passed from there and sufficient energy is added to the generate carrier in the depletion layer. So this is our depletion layer, right? This is the depletion layer to get the flow of current through the diode device. In this particular device, the electron should get flowed. So this is a depletion region. We try to pass the photons towards it, and we are getting the current from this particular battery. We are connecting to the battery, so we are getting the current flow through the device to get the sufficient energy which we are adding to generate the carrier in the depletion region. So this is getting the generated part of the carrier. Right? The light detectors are of APD, avalanche photodiode, which carried not just multiple kind of diode in that. It only used to generate the photons, photoelectrons get generated and get accelerated by relatively large reverse voltage, right? Because avalanche means what is occurs in the reverse region only. Reverse voltage and collide with other atoms to produce more free electrons. To get the more number of electrons, it's getting produced. And this avalanche is used to get the multiplication effect that make APD, avalanche photodiode, to more sensitive but also more noisy than the pin diode. So when compared to pin diode, avalanche use multiplication effects which make this avalanche photodiode to be more sensitive when compared to the pin diode. Because of that reason, this is also useful in our diode application part, right? So this is about our avalanche multiplication effect that make the APD to more sensitive. Next part is about application, students. So optical fibers, as we have learned about already, wide range of application in almost all field. Whatever the field you see, in almost all field we'll see. Some are being just specified below. In telecommunication field, in space application, broadband application, computer application, mining application, medical application. We have seen in detail in the previous classes as well about that particular part. Just want to tell you about very important part. Why it is so much important for us? So as you can see here in the military part, where actually it is using in electronics, in your microprocessor, IBM microprocessor designing in endoscopic. We have seen this part also, where the two optical fibers are used, one for light to illuminate the inside the patient of it, one for camera to send the image back to the doctor. So because of all these parameters, optical fibers are used. This is about today's session, students. Thank you very much for today's sessions. Tomorrow's sessions also will continue with the same concepts of optical communication. Thank you very much.